Hi, welcome back to part 2 of higher order partial derivatives. We're going to continue the process of evaluating higher order derivatives by looking at the following example. Let's say we want to find, oh my gosh, the partial with respect to x, then y, then z. Oh my gosh, that's 5 partial derivatives we're going to take. Given that our function f of x, y, z is z cubed y squared natural log of x. So when I want to take the partial derivative, well, the first thing I'm going to do is I'm going to take my partial with respect to x first. Remember, we're going to read it like a book from left to right. X, then y, then the two z's. When I take the derivative with respect to x, the z cubed and the y squared are my constants. I'm only looking at that natural log of x. So this is going to become z cubed y squared, and the derivative of natural log of x, we should remember that is 1 over x. If you forgot that, remember this, the derivative of natural log of x is just 1 over x. When we take the derivative again with respect to x, again, the z cubed and the y squared are constants, they stay the same. But the derivative of 1 over x, well, we should know this one too, is just negative 1 over x squared. If you forgot, maybe you can bring it up and use your power rule. So that's just negative 1 over x squared. So we're done taking the partials with respect to x. Now, let's take our third derivative. But this time our third derivative, you notice, is with respect to y. So everything else is a constant. The z cubed is a constant. The negative 1 over x squared is a constant. So my derivative then would be z cubed times the derivative with respect to y this time would be 2y times negative 1 over x squared. Now I'm going to start kind of cleaning this up so it just looks a little bit nicer. This is what? Negative 2 over x squared times z cubed y. So cleaning up is going to help us take the third derivative. Now the third derivative, now we're going to take, oops, sorry, that was the third derivative. The fourth derivative is going to be with respect to z. So now I'm going to go f, y, z. Now I'm taking the derivative with respect to z. And z is z cubed, everything else is a constant, so that's going to become, and I can bring that down, and we would get negative 6 over x squared, z squared, y. And now for my final derivative, fx, xy, z, bringing down the 2, we would get negative 12 over x squared, z, y. And that would be our fifth derivative in that order. So let's try another one. Now again, this is a different notation right here. So this is saying take the third derivative, the third partial derivative with respect to y, and 2 of them with respect to x. So of course the top here we just said is taking 3 derivatives. And the bottom down here says well, we're going to take the derivative with respect to x twice first. So when I'm looking at my function here, so another way that I could write this is I can write this as f x y. And that's what we're looking for. So I think this notation is sometimes a little bit easier to work with. So we take the first partial with respect to x, and this becomes e to the x y times, be very careful, chain rule, don't forget there's a chain rule right here. The derivative with respect to x just becomes y. Taking the derivative again with respect to x, we would get e to the x y. Remember, y is just a constant. But I got a chain rule again here, so I got to multiply by y again, and we get e to the xy times y squared. And now we're going to look at the third derivative. Now the third derivative is with respect to y. When we take the derivative with respect to y, though, we have to be very careful. There's a y in both terms. So we're going to have to use our product rule here. And that's, of course, just from calculus last year. So when we take the derivative, the first, which is just e to the xy, times the derivative of the second, which is 2y, because remember we're taking the derivative with respect to y, plus the second, which is y squared, times the derivative of the first, which becomes e to the xy. Be careful, chain rule, we are taking a derivative with respect to y, and that's just going to become x. And if you want to clean it up, we can write this as 2y e to the xy plus xy squared e to the xy. And you can factor that out if you want. And of course, that is our third partial derivative right there. All right, before we move on, let's talk, before we move on to a really cool theorem that we're going to talk about a lot in this class, let's talk about a French mathematician named Alexis Clairaut. Now, Alexis Clairaut, forgive me if I pronounce his name wrong, it is French. He was a French mathematician. Now, he worked on multiple variable problems. And one of the biggest contributions he did was what's called the three-body problem. If you look that up, it's a really kind of cool way. It's basically how do three objects gravitationally affect each other. The most common one we have is the Earth, Moon, Sun system. And it's how does the gravity of the Sun, the gravity of the Earth, and the gravity of the Moon affect each other. They all have some sort of effect on each other, and how can we predict their motions. Now, these are very difficult to solve, if at all possible. But Clairaut was one of the first mathematicians to satisfactorily predict the velocities and positions of more than one or three or more massed objects. Two is pretty easy, but once you get to three or more, it becomes a little bit more complicated. So we have a system of equations that he kind of came up. And another thing about Clairaut, Newton loved him. And Newton didn't like too many other people of his contemporaries, but Clairaut, he wrote praise after praise about this mathematician because Clairaut used a lot of his contributions helped prove Newtonian physics and what Newton was trying to demonstrate to the world. So Newton had very high praise for this mathematician, and that's a lot coming from Isaac Newton, the man who basically banished Leibniz from the math world, or he tried to. All right, so let's talk about what's called Clairaut's theorem. This is really big for us in multivariable. Suppose a function is defined on a disk containing some points. So basically, we're on a function. We have some xy coordinate, basically. If the functions, ready? If my partials, my functions, which are partials of f of xy and f of yx, are continuous on this disk, in other words, that the derivative, that it's a continuous function, then we can say that the partial with respect to xy equals to the partial with respect to yx. And all this is really saying is the partial of xy will equal the partial of yx. In other words, the order in which we take the derivative does not matter. And let's take a look at an example to kind of show that. So suppose we have z equaling e to the negative x squared y squared. We want to verify Clairaut. So we want to take the derivative partial of x with respect, the partial of x, then with respect to y. So if I take the derivative with respect to x, that's going to become e to the negative x squared y squared. Now don't forget, we got a chain rule here, so that becomes negative 2xy squared. Oh, it's ugly. If I take the derivative now with respect to y, we do have product rule, so we're going to have the first, e to the negative x squared y squared, times the derivative of the second. We're taking the derivative now with respect to y. We get negative 4xy plus the second, which is this negative 2xy squared, times the derivative of the first. E to the negative x squared y squared. The derivative of the inside chain rule, we're taking the derivative with respect to y. We get negative 2x squared y. All right, so let me go ahead and clean this up a little bit. Let me see right here. Cleaning this up, we get negative 4xy e to the negative x squared y squared, 2 negative positive, plus 4, how many x's here? X cubed, y cubed, and e to the negative x squared y squared. All right, so there's our second derivative. I think next time I'm going to choose an easier one to work with. But it's kind of cool to see for these really hard ones. All right, now we want to show that the partial of with respect to y, then with the partial with respect to x is. So let's take the derivative now with respect to y. So the derivative with respect to y would become e to the negative x squared y squared times chain rule. We're taking the derivative with respect to y, negative 2x squared y. And now we want to take the derivative of that function of our first derivative with respect to x. We are going to have to use product rule again. This is ugly. The first, e to the negative x squared y squared, times the derivative of the second with respect to x, negative 4xy, plus the second, negative 2x squared y, times the derivative of the first, which is e to the negative x squared y squared. Again, chain rule, ran out of room. With respect to x, we get negative 2x squared, negative 2x y squared. Oops, sorry, ran out of room there. And if I clean that up, you can notice we're going to get the same thing. Negative 4xy e to the negative x squared y squared plus two negatives, 4x cubed again, y cubed, e to the negative x squared y squared. And if you notice, these are identical to each other. They are the same. So therefore, we can say that the partials, the order in which we take the partials, really doesn't matter for us, and that's going to become very helpful for us later on. All right. Hope you enjoyed this video. Like that, smash that like button. I'll see you later. Bye bye.